Great, so that's all good. Great. Hey, so welcome back, everyone. So hopefully you turned in the homework on time. So I apologize. I've got a throat cold, so hopefully my voice will make it through the lecture. And I think I can still project enough everyone can hear me. But if not, please let me know. So in addition, the homework being due today, we saw on the schedule that next week on Monday, the data collection report is due. So I thought I'd just spend a couple minutes talking about what's going on with the data collection report. I often get a lot of questions of what do people actually, what do I actually want you to turn in? So basically, for the purposes of grading, and I'm happy if everyone gets all 10 points on this. I want you to kind of have something for each of these 5 bullets, and if you do that, you're probably going to be, you're probably going to get all 10 points. But the purpose of this is not just I want to have a task that you have to do just so I can give you a grade, right? But when you're doing the project, it often takes a lot of time to actually collect and find some interesting data. And so I want you to do this now. This is part you can do even if we haven't gotten to one of the techniques you're going to use for your project in the class yet. You can go and you can go and collect the data and start preparing it. And it's going to vary a lot between projects what you have to do. So some of you are working with data sets which are already in some nice clean format because they were from like this Snap website at Stanford. Often those are already nice and clean in a nice format. Others of you may have to scrounge it or scrape something or turn it from one format into another. And so if you're just collecting it and kind of and it's a nice format array, then you don't have to do too much. You may have to do more if it's one of these other cases, and in some cases that data collection is going to take longer than you'll have up until next Monday, and that's okay. But I want kind of to know your progress towards that so far at this point in the semester. I'm asking you these questions about how you obtained it and how large it is. Not so much because there's like a requirement it needs to be at least 1 gig to count for the class. There's nothing like that. But I kind of, these are things so I kind of make sure you actually did it. I kind of know what the numbers should be based on when people have done this in the past. And so the things I'm mainly interested in beyond just seeing that you've done this so far are that you've thought about, one of the themes of this class is turning things from some raw, messy format into some abstract type, like vectors or graphs or these matrices. And I want you to think about how you'd represent your data that way. So it says like what abstract data type, and I want you to think about how you're storing the data. And it may not fit it directly in one of these things, and it may be a combination of it. It may not be so clean, but that's the sort of thing that I'm interested in seeing you thinking about here. And so if you need to do something to convert it, then that's the sort of thing I'm interested in seeing. The other thing, which is often tricky, is this 5th part. How would you simulate the data? And so this is particularly relevant for some groups where it's hard to get a lot of interesting data that they want. They can only get some small subset of the data, so they need to generate some more data, which is synthetic, so that they'll be able to run some more interesting algorithms and do some bigger comparisons on. So in general, if you have a nice data set, I still want you to think about how would you, if you were to create an underlying model to simulate this data, how would you do that? What are the underlying parameters of the model that would generate it? And this may correspond with the sort of structure that you're trying to find, as the goal of the project. So it's kind of like a chicken and an egg problem. If you knew how to simulate it perfectly, then you wouldn't need to do any mining on the data. You would know essentially what the underlying parameters are, in some cases. But I just want you to think through this, and this will help you kind of conceptualize what sort of things what sort of parameters you would need to simulate it correspond to what sort of models you would want to find in the actual data. Or if you expect things to be clustered, you'd expect data to be generated from different clusters, not just abstractly, not just uniformly in some way. So if you're unclear about this, you can send me email or come talk to me at some point. Yeah.
So I guess to compare this to machine learning, machine learning might say, okay, to a certain point we have enough data, our classifier is probably approximately correct, but in data mining, how would you know how much data is enough?
Yeah, so the question is, in machine learning, you may know when you have a good accuracy, and where in data mining you might not, right? And how do you know how much data is enough for this? It's kind of often the case that the more data you have, the more low-level details you can actually recover. And so it's if there's one particular goal if you want to say you have a bunch of customers, you want to cluster them into different types, right? Well, if you only have a few thousand customers, you may only be able to get 5 reasonable clusters that you can know for pretty sure these are important types. But if you have 1 million, then you may be able to cluster them into 100 different types reasonably well, and those may be able to get more fine-grained kind of details to those, right? There may be so it may have 5 big clusters with smaller subparts in them, making up these 100 small things, and so it depends on what you want to do and how fine-grained you want to go with the analysis.
I guess that's helpful in the sense that way, because sometimes you just have this conglomeration of data right out there, and you don't know what it says, but you want to know, so therefore you don't have any understanding of what you might, a very, very clear view of what you might find, but you want to find something in it, obviously, and not just look for something random, but find something meaningful out of it. So how do you?
Yeah. So so this is again like a chicken and egg problem, right? Yeah. If you knew what the structures you were looking for, what you're trying to find, then you wouldn't have to go and find it necessarily. Often you have some hypothesis, you think something is there, and then if you can't, maybe you find it and you're satisfied, right? You find the data to verify it, and then you can refine it based on some model you fit onto that structure, so something like that. Other times you'll look for something, you can't find it, and it could mean one of two things. Either your hypothesis of some structure you thought was there is not actually there, or it could mean you just don't have enough data and often, if you have a small amount of data, it may have that structure may be there, but you weight it against the amount of noise in the data, you can't kind of see that it's really there because the noise is overwhelming it. And so, yeah, so you can either draw if you find it, then that's great. If you don't find it, then you should be careful not to say it's not necessarily there. Or to say that look, the data is really noisy, and at least things were not as clean as you thought they might be. For these class projects, it's hard. You're going to collect some amount of data and try and do something with it, and a lot of people in the class have been successful in the past at succeeding in their goals, but not everyone is, and that's okay. I'm not going to give you a bad grade because your data ended up being, the data was noisier than you thought it was going to be. But try and do it with the data you have, and see what happens. So great. So any other questions on the data collection report? All right. So. Let's see. So then today we're still talking about clustering, So we'll be talking, where in the past we were talking about data points where there is a distance between them. The setting today is going to be dealing with graphs. How do you do clustering on graphs? And so I'll talk about, we haven't really talked about graphs much in class before, so I'll do some setup talking about them. And then given that we want to do this, we'll talk about these methods which are called these spectral methods for clustering. And the spectral refers to using the eigenstructure of the graph. And so to do that, what we'll do is we'll go from some graph, we'll convert this into a matrix. From the matrix, we will look at the Laplacian, Laplacian of the matrix, which I'll explain what this means, and then we'll get the eigen vectors of this Laplacian, and basically the eigenvectors will tell us how to do this clustering. Okay, and so there's going to be kind of this process. Some steps will be kind of mysterious. So I'll try and explain why they're working, and we'll get at clusters in ways which are very different than we've done in the past couple of lectures. And the first one that we talked about was this hierarchical clustering, and this was kind of what's sometimes referred to as a bottom-up clustering. So we started with a bunch of points, we merged some together, like this. You started from the bottom down individual points, and you built up, right? You're going kind of up like this. The second type was different. It was based on these assignment. Right, this assignment-based clustering, where once we identified these centers, then it said which points were in which cluster based just on the closest assignment. So the third type will be kind of in contrast to this these other two. It's going to be a top-down. And so, like here, you can think of building this hierarchy again, but instead of going from the top up, you're going to kind of think of going down. So the first step is going to be finding this split of the data into two parts. So you can have this left part and the right part, and then you just recursively apply this, and this will give you a clustering. You have a question?
So is the hierarchy always be a binary tree?
So it doesn't need to be binary tree. Yeah. So it can be in the methods we talked about. It was binary, but you can merge multiple things together at once, and that's fine. There are just different variants of how you run it. Like I said, there are hundreds of variants of how you do these clustering algorithms, and sometimes they have small different advantages over each other. They don't need to. In this case, again, the ones we talk about today with the spectral-based ones are going to be the sort of things we'll construct will probably be binary. But I'll mention some ways that you would do it so it's not binary. Right. So we're going to do this theme, and and kind of the main step we'll look at is how to split our data into two parts. Right. So again, if we're doing just point sets. Right, the core thing, and maybe it was such that there were multiple kind of clusters here. Our goal is to find some way of splitting it so these are on one side and these clusters on the other, and then maybe you do this hierarchically. So then you split it within this after this first split. So remember, when we're doing these nearest neighbor searching, they were again building this hierarchy from the top down, and we're going to do something similar. And you can do this with spatial points, and I'll mention kind of a clean way of doing that later. But this is kind of kind of the most intuitive way to do it for graphs, which is otherwise kind of harder to find these clusters in the graphs. Okay, so just like before I talk about graphs, just I assume that people have heard of graphs before. Who's not heard of a graph? People know if what it means for a graph to be connected, right? So right. So let's say this a little differently. Let's say you have so typically if you have a graph, just to kind of fix some notation if you're not used to it, usually you say it has these set of vertices and some edges. Vertices and edges. And so then you would often think of drawing these vertices as points. Right? You can think of drawing them as points, and then you would draw these edges in between these vertices. And so what is kind of different from everything we've talked about before in class is that the place where I draw the vertices, does not really matter, right? There's a whole field of how best to draw graphs. There's a graph drawing community. You're trying to draw them so you can kind of see the structure kind of natively here, but the position doesn't matter. All that matters is which vertices are connected to these other vertices, right? And so you just want to store this structure, and there are data structures for doing this. Typically, you would think of this vertex set, say maybe being v1, v2, up to vn, and so you can then just store these as numbers 1 through n, and then you would think of having this edge set. Again, it's a set, so it's curly brackets, and then within each edge set, you have like 2 vertices. And so this is a set of these sets of size 2. Right? An edge is a set of size 2 then. Like this. And so this would, again, be like edge 1, edge 2, up to usually edge m. Right? So this would be kind of how you think of storing it. And again, this is one of these things that kind of has this. It's kind of it's mathematically captures everything in the structure, but it's not necessarily easy to work with. Remember when we worked with the sets, we went through this business to create these min-hashing vectors because these were easy to quickly compare, and you can do like these quick nearest neighbor searches with them. With this edge set, it's kind of similar in that this format captures everything, but it's not really that easy to work with. Okay, so I'm going to show you an example here. All right, so I made. All right, so I have some examples on slides so that it's a little bit easier to kind of go through this stuff. So here's an example graph. So now my vertices I've labeled A through G as letters here, and they're edges, right? And so I can represent it as just the vertex set and the edge set. But what's often kind of more convenient to one other way to write this down is to write this down as this table, and then you say that okay. So then if I have this table, so I can look at one of the elements. This is a 1. That means that there was an edge between A and B that correspond to this edge here. Right? If I have a 1, if it's an edge, this edge is a set. That means I don't have any direction on this edge. There's a thing of a directed graph. That means it goes from A to B, but I didn't have a direction. That means that it should also appear in the table here. So this table is going to be symmetric. And then I can think of this table actually as this matrix. right? The table is kind of like a matrix with numbers in it in this nice way. And so I can think of this now as this matrix. And this is a way of captures all the information in this graph. Okay, so what's kind of a downside of representing the graph here, this graph here as a matrix instead of just this list of vertices and edges? Yeah.
You'll take up a lot more space if it's a sparse graph.
Yeah. So if this graph is sparse, and by sparse, you know, the idea of sparse is that it has is, you know, there's different ways of defining precisely, but it's almost all zeros. The zeros are where I don't have any edges, right? So if I look right here, G and C, there's no edge between G and C here. There's nothing in this graph. There's nothing. There's no. You know, there's. See if I can scroll a little bit here. There's no. All right, this isn't. Okay, so there's no edge between G and C here, right? In this G and C in the graph. But I had to represent this as a 0 in the matrix still. So there are ways of representing matrices sparsely. If you go in MATLAB, there are special representations of the matrix as sparse, and you can get so it actually doesn't take up as much space. But sometimes when you want to do operations on it, sometimes those can be done using the sparsity, sometimes they can't. And we'll actually talk about some matrix approaches later, ones that can, some basic ideas of how you can take advantage of the sparsity and sometimes how you can't. But so it's kind of a bulky way of representing the data. But what it will be nice about it is that it will allow us to kind of use some machinery from linear algebra in order to tell us how to cluster this graph. Okay, so all right, so let's go back to these slides here. So when we have this graph here, so let's say this was my example graph, as I've drawn this one here. When I say I want to cluster the graph, what would make sense as a way to cluster a graph? What would that, if I say that, in what way would this make sense to you? What do you think I'd want to do with that? Yeah.
High amount of connectivity between associated things and then low connectivity between things outside.
Yeah, okay. So you know, when we first talked about clustering, we talked about these ideas of the split and the width, where width was kind of saying inside of a cluster, I'm going to have a lot of similar things, and between the split was saying between different clusters, I don't have a lot of things, or these things are not similar to each other. And so in graphs, even more, before you even say that, you know, when I say clustering, I basically mean, so clustering, even more basic than that, clustering on the graphs equals the clustering of the vertices. So you could potentially think of clustering the edges in some way, but often the vertices are the points of information, and the edges are like the connectivity between them. So now, kind of, why is this interesting? Well, kind of a lot of these graphs come up where you're, you know, now classic example is like this represents like a social network where all the nodes are people, like this is Facebook, and then if you're friends with someone, then there's an edge between them, right? And then the vertices, which are really well connected, would represent a cluster of people, right? There'd be maybe very similar people. They're all in the same, you know, network of friends. And so in the Facebook graph, you tend to see clusters of certain types. The largest clusters are basically of people in different countries. Like, you know, the people in Brazil have a tighter cluster than the people in the U.S. Now, there are a lot more people in the US, but that's kind of the high-level clusters. And then you'll see other different, some other different communities of people. Often these are based on like where these people went to school. This was much more prominent before. When Facebook started, it was, if you've seen the Social Network movie, it was piloted in various universities. And so everyone within the university would be very well connected with other people, but to be less so across different universities. I kind of missed the Facebook wave. This kind of dates me. Well, when I was going to college, it was the year before Facebook went to that college, and when I went to grad school, it was the year after. So I'd missed all the hype in both places, and so I shouldn't say this, but I still don't have any account on Facebook. So if you try and friend me, I can't do anything like that. But my wife has 2 accounts, so that kind of makes up for it somehow. So you're clustering these people in the social network, or maybe these are different companies and they're connected because they've had some business transaction, or they're countries that have traded with each other. You have some sort of these edges capture the relationship, and the more relationship, think of the more edges, right? So you want to find entities which are similar because they have more relationships with other things in the same cluster, right? So ideally, we'd want to do something like maybe I should have gotten this vertex. Okay, fixed it. All right, this is one cluster, and this might be the other cluster, and there's only one edge which is going between them. Right? So we want something like this where inside of a cluster we have a lot of edges, and that's true for both clusters, and going across the clusters we have few edges. Right? So let's look at this a little bit different. Let's try and formalize this notion here. Right? So again, let me draw one of these example graphs here. Okay, so the idea when you're clustering this, again, we're just splitting in 2, and then we can recursively do this to split into more parts. So the idea is we're going to kind of split the graph and create some sort of set of these vertices. We'll call this set S, which will be a subset of V. And then S complement is going to be V set minus S. So when you have a set and you do this, it's everything that was in this set that is not in this set. So that gives you the complement S. And so these are the 2 clusters, S here and S complement, which is everything else. Okay, and so there are going to be kind of 2 properties we want based on the split and the width. One is often called the volume of S. And so to measure the volume, to measure how much connectivity there is inside of a cluster, how would you so this is kind of define the notion of the width of a cluster. How would you kind of define this notion? How would you say how big or how connected is a cluster? Yeah.
The maximum number of edges you need to go from one vertex to another.
Yes. So one way you could do it, it would be something like the diameter of the graph. So that's what that's called, and that's the suggestion was the maximum length of any path from one vertex to another. So inside of here, it would be length 2 to get from this vertex to this vertex. It'd be 2, right? So on this side, it would be 3 to get from this vertex to this vertex. So it would take, or no, it would still only be 2. You could do it in 2 steps again. So that's a perfectly good suggestion. It's not standardly what is used here. Yep.
Like the ratio of actual edges to possible edges?
Yeah, so the ratio of edges to actual to the possible edges, and so this is pretty close to what we're going to do. So instead of the ratio, we're just going to count basically the number of edges. So there's something based on the ratio we'll talk about in the one of the last sections in class on finding communities in graphs that use something a little bit more similar to that, but it's just going to be the number of edges, and specifically they define it with, say, with at least one endpoint in S. Okay? So in this example, the number of edges is 1, 2, 3, 4, 5, 6. This one that has one endpoint in here is counted in this volume. Okay, so the volume of S here in this example is equal to 6. If it was just with both endpoints in S, then the volume would be 5, but it's one endpoint in S. Okay, and then the other thing people look at is the idea of the cut between two sets of vertices, and often this is between S and S complement, but you could define this between any two sets. And this tells you something like the split of the clusters. You want some quantity that tells you how big is this cut, and if you take in an algorithms class, then you probably have looked at these problems of graph cuts, right? And so this is just the number of edges with one endpoint in S and the other in S bar. Right? So in this case, the cut here is going to be just this one edge. This is the only edge that goes across S and S bar. Right? So in this case, it's only going to be 1. Right? So one way of thinking of doing this clustering on graphs, and this used to be kind of a fairly common thing to do, especially on smaller graphs, was to just try to find to just look at this graph and find the min cut in the graph, right? Who's heard of like these min cut algorithms, right? In these algorithms class, right? You want to find the minimum cut, the cut that crosses the fewest number of edges. So you want this cut to be as small as possible. So if you just found the min cut in this graph, it's possible that you would actually find this separation. You would say, let's cut this one edge. It separates the graph into two parts. But the problem is that's not the only min cut, right? Where's the other min cut? Right? There's another min cut over here also has only one edge, and you just have one vertex over here and then 7 vertices on the other side. Right? And so this is, here it's not so bad, right? You can just look at a couple of these and pick whichever one is better. But on very large graphs, this becomes doing this becomes much more problematic. So, kind of, if you end up looking at these large graphs, they try and draw them like I drew the graphs before. They try and draw them so you can see all the vertices, and they ended up looking kind of like these hairballs. They're so huge, you get a bunch of edges like this, kind of, who knows what's going on here, and then there'll be edges off here which will have, where there's a vertex which is only connected to one other vertex. And so then if you do one of these min cuts, all you're going to end up doing is saying this quantity is S and everything else is S bar. And this isn't really that helpful. You said here's one vertex and then here's everything else. Right? So just doing this cut by itself is not a great way to do it, especially in very large graphs. This happens all the time. So you somehow want to balance that the volume of both sides is large and the cut is small. Okay, so you want both the volume to be large and the cut is small. And so there are a couple of ways people have kind of formalized measures for this. We'll mention one way that's called the normalized cut. And there are a couple of similar ways to define this, and they both will map to different algorithms, but this is the one that kind of tends to work like a little bit better than other ones to optimize and when you're actually doing this in practice. So the normalized cut is defined as the cut between S and T. So T here is going to be like S bar, so the complement, over the volume of S plus the cut of S T over the volume of T. Okay, so you're going to want this normalized cut to be small, just like you want the cut to be small. So if the cut you find between S and T is going to be large, then it's going to cause both of the terms to be large. And if the volume is small, right, then so if the volume is large, you're dividing by this large number, right? So if the volume is small, you're dividing by a small number, and so you're gonna get something large. And so if either of the volumes is small, like if instead here I'd said, okay, well this volume is small, but I can instead say, well, let's make this guy S, and then it's okay. I need both sides to be small, right? So if either of them is going to be, I want both of them to be large. So if either of the volumes is small, then the corresponding term is just going to shoot up and be very large. So this normalized cut is a way of balancing both the volume and the cut. And so then the goal is to find a subset of the vertices that has as small a normalized cut as you can find. Right? So that makes sense, kind of as a measure. This intuitively seems like this is a reasonable thing to try and strive for. If you did find such a normalized cut, then you would have two roughly equally large sizes, which is good, and you would cross a small number of edges. Right? So now if I look at these two examples, for this version where this guy is S, then the normalized cut between S and S transpose, N cut of S bar, this is going to be the cut, which is 1, over the volume on the left, which is going to be 6, plus 1 over the volume on the right, 1, 2, 3, 4, 5. So 1/6 plus 1/5. This is, what is this going to be, like 11 over, 11 over 30? Okay, it seems small. Let's look at what is the normalized cut of this second cut that only has one thing on the side, right? So let's call this instead this guy to be S prime, and then you can look at S prime S prime complement, and now I'm going to have that the N cut of S prime and S prime complement is going to be so S the cut here is 1, and the volume is 1, right? That's why I included if any endpoint is in S, right? Otherwise, the volume would be 0, and this would be infinite, and that'd be kind of weird. So that this one is 1 plus 1. That's already very large. The other side is going to have still the cut is 1, but the volume is going to be large in this side. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this value is going to be equals to 1.1. Right? So now 11 over 30ths is basically 0.35 or so, and this is 1.1. So now this is much smaller. It's clear that this first cut I showed is a much better way of splitting the graph into two parts under this normalized cut metric. And that's what we wanted. We want it so we can, for doing this recursively, we want to make progress. We want them to be kind of somewhat balanced. And this normalized cut will force us to balance it as we're cutting it. Okay, so now that we've defined this nice measure that we'd like to use, how do we find a good normalized cut? So what is a good way to do this now? How many possible different cuts could we make of the graph? Yeah, right. So it's the number of cuts. So the number of cuts is going to be equal times 2 times the size of the vertex. And you can see this because each vertex you can say is 1 if it's in the set S, or it's 0 if it's not in the set S. Then you can label it as a binary number, and you get 2 to the n different binary numbers, right? So there's 2 to the n different cuts. We can't check all of these different cuts, right? There are some various algorithms that trying to kind of search in this space. You can do things like, like genetic algorithms or something silly like that. But there's this really cute way based on these matrices, which is very effective, right? So if we think of this graph now as a matrix, there's a good way of figuring out how this cut. Now, it's not going to give you necessarily the optimal answer, but it's gonna try to give you a way of splitting the graph that is going to be minimizing this normalized cut, and kind of optimizing in the way based on the matrices I'll explain will give you a good answer based on the normalized cut. Yeah. What, can you say that again?
Would it help if we figure out the minimal cut?
The minimal cut first. Yeah, so it seems like it'd be a good starting spot, right? Because here there were 2 minimal cuts, and one of them was actually what we wanted. But in practice, these large graphs, all the minimal cuts are going to look kind of like this. Or there's going to be just cutting off one vertex. And those in most realistic settings, those are not going to be that helpful. You really kind of, so you need to look at this different cost function, and in general, you can't say any useful relationship between them. It's an interesting way to start, but it turns out it's not going to work. So you can't use these algorithms for finding min-cut, right? There's all these cool flow algorithms that work, and there'll be a way to think about a version of these as a flow, but we'll talk about it a different way based on this normalized Laplacian, which does not have quite the same flow analogies. So the kind of the goal we're going to have, and how to do this, use the matrix, is we're going to somehow take this graph, and the goal is going to be to some way project all of these vertices onto some line in some way. This is just a high-level view, and then we'll come back and see it. Think of all these vertices are going to be on the line in such a way that if I either I take the midpoint on this line, there'll be some notion of 0. This might be a good cut, or I can kind of check all the cuts on this line. Because there are only n vertices, I can just scan over them and consider all the possible cuts. I'm going to somehow put all these vertices on a single one-dimensional space, and this will tell me how to do the cut. And that's kind of going to be our progress. And the spectral method will be the way that best puts the vertices on a single line so that the cuts tend to minimize this. All the cuts at any level tend to minimize this normalized cut. It doesn't guarantee we get the best one. It has kind of a slightly different objective, but it ensures that we're getting towards the right way of doing this. Okay, so how do we do this? How do we get all these vertices of the graph onto a line in a way that makes sense, right? I said before, when I drew the graph, it didn't matter where I drew them. Right? So we're going to see a way that kind of, so it makes sense how to draw the graph so it corresponds to the cut that you're actually interested in. Okay, and so let's, so again, so the way to do this is going to be, there's a way to clear the screen here, but, okay. There's a way to do this by thinking of this as this matrix. Okay, so we're going to create what's called the Laplacian of the matrix, and I'll kind of step through this. So who's heard of the Laplacian of a matrix before? Okay, so a few of you have heard this. Now there are multiple ways to define a Laplacian. We'll talk about a normalized way and an unnormalized way, and the normalized way will correspond with the sort of cut we were talking about. So the first thing to do is to kind of create two sorts of matrices. The first one we already had, which was the adjacency matrix. This was the same thing we constructed before, where you can think of the first column as representing this vertex A. And the first row is also representing the vertex A. And so the second row is B, and the second column is B, and so forth, right? So each of these, the ordering of this doesn't matter so much, but I'll do them in alphabetical order in all these. So this is the matrix that we represented the graph with before. It's called the adjacency matrix. There's another type of matrix you might want to do, which is called the diagonal, or actually this is often called the degree matrix. The degree matrix, and what it does is every element, so this represents bth row and bth column, it only has elements, it only has non-zeros on this diagonal, and the value in here is the number of edges. So B has 2 edges, so there's a 2 here. 2 edges that are incident to it. C has 3 edges, right? Has 3 because there are 3 edges here, right? So that's how I get this degree matrix. Okay, and we'll call this matrix D. Both of these are going to be n by n if I have n vertices, right? Does this make sense? Yeah? Okay. All right, so, okay, so now, so then to get these, to get the normalized Laplacian, we first need to do something we need to do something kind of funky to this to this degree matrix, and we're going to take the matrix to the power -1/2. So in general, there's some defined operations where you can take a matrix to a power, and we'll look at some of these later in class. But and it makes sense if that's a positive integer in a pretty nice intuitive way. If it's something else, like it's a -1/2, well, if the matrix is a diagonal matrix, that means that you actually just perform that operation to each thing that's on the diagonal. So then, if you remember before this, so this number here, this is 1 over square root 2, right? So this is equal to 2 to the -1/2. This number is 1 over square root 3, which is 3 to the -1/2, right? So 1 over square root of a number is equal to that number to the -1/2. So that's how I got these numbers here on the diagonal, right? So I do this d to the -1/2, and I get this new matrix, all right? And then finally, the normalized Laplacian is defined like this. It's the identity matrix, which is just 1s on the diagonal and 0s elsewhere, minus this d to the -1/2 times a times d to the -1/2. So this is a little bit confusing what's going on here, but there's an unnormalized Laplacian which has some more nicer intuitive meaning, but it doesn't correspond with the normalized cut as well. So this is how you define this. You can do this inside of MATLAB or a lot of other languages now. When I first started teaching this class, like 4 years ago, it was hard to do a lot of this matrix operation cleanly if you weren't using MATLAB or some version of that. Now, Python and Julia have these nice languages for matrices that you can probably do this pretty easily in there as well. But you can just kind of do these operations in MATLAB, and you'll end up with a matrix that looks like this. Okay, this is kind of mysterious, and then we're going to do one more thing to this matrix. We're going to find the eigenvectors of the matrix, right? So if you have a matrix L, then an eigenvector of L is such that if you multiply this matrix by V, you're going to get back. So where this is a matrix, and this is a a scalar. So you're going to essentially get back this matrix, and so there's kind of there's something a little bit arbitrary here. You can actually multiply this vector, and it's still kind of an eigenvector by like so you can make so the scalar is always 1 is one option of kind of a canonical way of doing this. So then that would work. So if you multiplied this every entry in the vector by lambda, then you would say this matrix times this vector gives you back the same vector, right? So this should be kind of strange. If you're usually when you multiply a vector times a matrix, you're kind of transforming it in some way, and these eigenvectors are these very special vectors that you get back the same thing you started with. Right? And the number of eigenvectors corresponds with the rank of the matrix, and we'll actually talk about these. They're kind of related to the singular vectors of a matrix, and we'll talk about these and the meaning of these in a different context a bit in a few weeks later. But so we want to calculate these eigenvectors, and again, calculating these you can do easily in MATLAB. If you can write the output of it's going to give you a matrix V and a vector, and I'll use lambda here, is going to be, if you type in eigen of L, should be these should be parentheses. In MATLAB, it'll just give you all the eigenvectors and all the eigenvalues. So this would be the scalar is the eigenvalue, and this is the eigenvector. Typically, when they output them so that the norm of this vector is 1, and then this eigenvalue has some meaning to it. Okay. All right. So let's. So if you do this, the actual eigenvectors and eigenvalues you're going to get are going to look like this. Let me get these out of the way here. Right, so these are going to be, so now each of these columns, each of the columns here corresponds with one of the eigenvectors. And you'll note that each of these is normalized. If you squared each of these entries, add them up, it's going to be 1. And then the eigenvalue is up here on top. So typically it's presented to you so the first eigenvalue is going to be 0, and so and this eigenvector is typically not very interesting. But the second eigenvector, we'll call this V2, is going to be a very interesting object here, and then you get V3 and so forth. So V2, and these are sorted so the smaller the eigenvalue comes first. And so the one with the smallest eigenvalue is going to be the, other than 0, is going to be this second eigenvector. And so this vector is going to somehow tell us how to kind of draw this graph. Okay? So, and how to draw this graph so then the cut becomes apparent, what the right cut is in the graph. Yeah, so let's, so I've got another thing prepared here. Let's, so if I now, let's see, right, okay, so what I'm going to try and do here is I'm going to take this graph and now draw it using, now I've copied over the second and the third eigenvector here. And so how I'm going to draw it is I'm going to assign each of these values. Like if I look at B here, B is going to be given a location here. And so it's going to be given a location along the x-axis based on this value v2. And so what I'm going to do is I'm going to look at this value, the second value in this eigenvector, and I'm going to get 0.36. And I'm going to do 0.36, and then I'm actually going to scale it by 1 over lambda 1, which is this 0.25. So it'll be 0.36 times 1 over square root of 0.125. And that's going to give me a location here of B on this x-axis. And I've done this with each of these, with each of the vertices in the graph. And I've done that not just for the x-axis, we're using the second eigenvector, but I'll give it the y-axis with the third eigenvector just so you can see them spread out a bit more. But I could do them with just the first eigenvector as well, and it would, it turns out that's all you're going to need for the spectral clustering, right? What I've done is I've spread them out, and I've said, these points are further. This set is furtr away from this set over here, and there's a 0 spot on this graph where all of, if I look, these values E, F, G, and H are all negative, and these values A, B, C, and D are positive. Right? So all these are positive, all these are negative, and then to create the cut, all I'm going to say is the ones which are positive, these are going to be an S. And the ones which have a negative value are going to be an S complement. And basically this is how you do, this is the simplest way of how you do this spectral clustering. Okay, so there's kind of some kind of strange intuitive steps. You're creating this Laplacian vector, or this Laplacian matrix. And then the first eigenvector of that tells you kind of how to do the cut. Yeah?
Why are we looking at the smallest singular value, smallest eigenvalues? Why not the
So the smallest eigenvalue. There's different things we'll talk about a little bit later in class. We'll call these the singular value decomposition as well. And there you typically want the largest singular values. The largest singular values correspond with the smallest eigenvalues. Kind of there are different ways of writing down this, but often 1 over the, I think 1 over the square root of the eigenvalue is going to be, I think, the singular value, right? So this quantity right here, this is the singular value associated with so this eigenvector is going to, I think, going to be the right or the left singular value vector, and then you want the smaller singular value would tell you the smaller singular value is a larger eigenvalue, right? And so kind of what you're kind of doing here in an intuitive sense, and I think this is more clear using the singular value decomposition, which we'll see in a few weeks. But the first eigenvector is telling you, it's trying to capture the flow of information going across this graph. Okay, it's telling you how this information flows, and if you were to write this flow down in just one dimension, the best way to do it is this first singular vector. That's capturing some amount of the flow. And with this formulation, there's this connection between like these like the resistance in these electrical networks, and there's some connection you can have there, and I'm not going to go into that, but it kind of tells you how much resistance there is, or how much kind of electrical current would flow across this part of the graph under a certain setting. And so it's the first one is telling you how to spread out this graph, right? And so if you notice, when I drew this first this data, I plotted the x and the y coordinates here based on the first the second and the third eigenvectors here. And the second eigenvector, which comes first, spreads out the data, is spreading out a lot more than the third one is. Right, once I've normalized by the 1 over the singular value, the 1 over the square of the eigenvalue. Right, and these are all normalized vectors, right? So they really are spreading out the same individually, but when I normalize by when I normalize by 1 over the square of the eigenvalue, that tells me how much spread I'm actually getting. And that's kind of, yeah. So, question?
So with this, you're basically you're clustering the graph into two separate sets or two separate graphs. And then do we recurse from there or iterate from there, doing the same thing over onto the graphs that we just divided and continue on that way?
Yeah, so there are a few ways of doing this, and they have different advantages and different disadvantages. One of them is definitely saying, okay, after I've done this, now there are two subgraphs, and I'll ignore this edge. So let's say it's if we say that subgraph is induced, then that means I look at the vertices and only the edges between those vertices. So I look at the two induced subgraphs, and I recursively start this all over again. And this one will give you the best splits at every level, because it's, at the top level, this gave me the absolute best split. So I want to do that again because that's the best way to do it. But it's slow to recompute the matrix structure and the Laplacian and the eigenvalues of it. So often what people do in practice is something else. Though there are a couple ways of doing this. One is say if I plotted this using the first two eigenvectors, then I actually already have 4 clusters here. I've got this one, this one, and this one here, based on the signs of the first and the second eigenvectors. So if these two, or C is the only element which is positive in both, so it's in its own cluster. G and E here are negative in the first one and positive in the second one. So I already have a 4-way split. I could do this as well, and I could go 2, or if I use the first, the second, third, and fourth, I get an 8-way split. And maybe some of these will be empty. Actually, in practice, there's sometimes we'll have an empty an empty quadrant if the graph isn't too big. But on a large graph, they'll probably be full. So that's one way of doing it. Another way is, once I have these coordinates, I'm now in a space that looks like it's actually have a particular location of these points. I can now use something like Lloyd's algorithm for k-means clustering on this data. So people say, okay, first do the spectral mapping into a 2-dimensional Euclidean space, and now I can run k-means on that. And so that'll give me a clustering there as well. Sometimes what you have with more complex graphs is you'll have some parts of the graph which are kind of crossing over this boundary, just on how this embedding is working. It may be like this, and so it may make more sense to kind of cluster these together instead. Yep.
So I've got a question. So is it possible that there are no negative eigenvalues there? How do you escape them?
Oh yeah. So a property of these is that they will. Forget exactly what how this is specified, but all the eigenvectors will kind of have a balance in that some will be negative and some will be positive. Right? So it'll always have some. They'll always be balanced around 0. I forget what is that property that you can see that with, but there's some way. It's always going to split them around 0. But actually, what you bring up is a good point. You don't always want to split at 0. In practice, what people do when they build kind of there are these kind of large software out there that does this in a large graphs really efficiently by kind of maybe they'll approximately compute the first eigenvector in a faster way. To find the cuts, they won't just necessarily split at 0. What they'll say, once I have a one-dimensional ordering, I can then look at all of these cuts in linear time and consider which one actually gives me the best normalized cut. And this will often work a little bit better. Sometimes you get, if you look at this ordering, you may get a bunch of points here, and then you'll look at and get some points like this, right, where one point is out here that balances it, but the best cut is actually to map this guy with these guys because there's a big gap here. And so you'll put the normalized cut someplace here as well instead. And if you're doing something that you're at least assigning a coordinate to every data point, that's already taking linear time, so making one more scan over it to kind of compute this normalized cut, you can do it. You have to keep track of the edges as well, but you can do it fairly efficiently to kind of just scan over these and so you can check all these. And this is normally what people will do if they're doing just this one cut at a time. They'll either do that or they'll use the first two or three eigenvectors and then do k-means clustering once they've embedded it, because that also works pretty well. And so if you've noticed this is kind of our first kind of way with that we'll do dimensionality. Like reduction. So if you've heard this term, or maybe you think of this as embedding. So you're taking this graph and you're embedding it into this space, into this two-dimensional Euclidean space. Once you're in this two-dimensional space, you can run algorithms made for this, like k-means clustering, which operates well in this low-dimensional Euclidean spaces. Right, so this is kind of a very powerful technique. You're taking this abstract graph, which has this very straight structure, and giving it the data some nice Euclidean structure, where you can then treat these vertices as points again. Right. Okay, so this, yeah. Okay, so there's one more thing. So this kind of definition of the Laplacian is often the one that gets used and kind of works well with this definition. It maps to the definition of the normalized cut, which is kind of the most intuitive way to work with. It's not the only way of defining the Laplacian, and in some ways it was kind of this unintuitive beast, right? We took this, let me erase all this nonsense first. So what we did is we, right, if you go back here, we did this thing where we created this Laplacian by getting this this degree matrix, taking it to the -1/2 and multiplying on the left and the right side of this adjacency matrix, 1 minus. This is kind of strange what's going on here. Around the time when this ideas of spectral clustering were developed, there's a different line of work that used a different form of the Laplacian, which I'll call the unnormalized Laplacian. And it's much simpler to kind of write down and understand. And this one is just the degree matrix minus the adjacency matrix. So you may have seen this form before. And they don't always, when papers write about these, they don't always say which form of the Laplacian they're using. Sometimes they're using this one, sometimes they're using the other one. And they both will work roughly the same way. You can use this form of the Laplacian, and it will give you, using the first few eigenvectors of this Laplacian, will also give you a pretty good embedding of the points. But it won't be as optimized towards the normalized cut. There's some other measure you have to map it to, which is less intuitive. The nice thing about this form of the Laplacian, it's a little bit easier to understand what's going on. So you can see there's a nicer structure in this matrix now. Every row and every column is going to add up to 0. Right? So if I look at right? So if I look at this row, it's got -1s from the adjacency matrix, and a 3, which is a positive from this degree matrix. And this should make sense because for every edge coming out of A, it's going someplace else, and I've subtracted that off from the adjacency. And there were 3 edges. That's because the degree was 3. So these kind of cancel out. You can think of this as there's kind of water flowing into this of degree 3, and then it's going out in these other directions. There's you could think of this as a flow. There's water that's flowing around the system. This tells you, maybe along the rows, tells you where the water is coming in from. Okay? And there are 3 things that are coming in so that I get a degree 3, and then I send it out along this column. Or maybe you can think of it vice versa, depending on which way you want this flow of water to go. And so this Laplacian has this nice property like this, and we'll actually look at. So far, I only talked about here of these graphs which are undirected. Later, we can talk about ways where there are edges flowing from one vertex to another, and we'll talk about these in the last last section of lectures in the class on graphs. And then you want to think about this flow. You want to think about how much stuff is going from C across to E here. And it's matter you may have stuff flowing into C, and then it's going out to E, and maybe some of it goes back down here, and something like this. So I could think about this as if I have directions in here, the adjacency matrix would capture only these directions as well. And so then the cut is something where, in order to get from this side to this side, this edge becomes a very important edge in separating the graph. If I cut this, I lose a lot of communication. Where if I cut this one, I don't lose as much communication, what's going on here. And so we'll talk about this much more formally when we talk about Markov chains and the PageRank algorithm, which is kind of built on these sort of ideas. But this is a little bit easier to see with this version of the Laplacian. This would be the unnormalized version. Just to go through this, let's see what happens when I do the embedding and the clustering of the graph using this unnormalized Laplacian. Then I can, if I take the eigenstructure of this L0 matrix, I'm going to get this structure instead. And now there's also some other cooler structure going on here. There's this this first, when you use this unnormalized Laplacian, again the first eigenvalue is 0, but the first eigenvector is always 1 over square root n. It actually captures no information here. Before there was some kind of stuff going on here, but it was really kind of meaningless. In this case, it's kind of just the average of everything. It's putting everything in the same spot. Whereas, and then for all the other ones, it's working the same. When you use the unnormalized Laplacian, then this second eigenvector v2 is called the Fiedler vector. And so this tells you kind of something about kind of how important, it tells you something important about this flow of this information on the graph, if you're thinking of it like water. Okay, and then so if we use this to do if we use this to do this embedding using the first 2 eigenvectors, you're going to get a graph that is going to look like this. And this kind of, in some ways, it's more intuitive. It's trying to constrain this flow. So what's going on is this this value h, even though it's connected to f here, it's kind of really far away from everything else. If I were to cut this off, it's not really going to change how the graph can flow very much. Where this one is more central. There's some stuff between C here and E, right? It's kind of trying to spread this graph out and draw it really well So I put things kind of only close if there is an edge connecting them. If there's no edge, I want them essentially to be far away as possible, kind of under some constraint that kind of these vectors here are normalized in -1 to 1. The other possibly interesting thing to see here is A and D. If I look at these, both A and D are in the same spot. This was true with the other embedding as well. Why are vertices A and D in exactly the same spot here when I do this embedding? Yep.
Because it have the exact same set of edges essentially.
Yeah, that's right. If I looked at the edge set, they're both connected to C and B and nothing else. Oh, and they're also both connected to each other and nothing else, right? So from the graph, there's no way to distinguish them, right? So of course they're gonna, when I try and embed them, it's gonna end up on exactly the same spot. And so really, because they have the same connectivity, it's hard to say which way to put one and which way to put the other. If you go back and you look at, here, these are A and D, this first and the fourth row here. They do eventually get in the last singular vector here. They do get different values, but everything else is 0. And this is basically arbitrary what the sign is. This isn't really telling you any information. There's like not much else going on here. So this is at the very end. If you looked at the previous use of the Laplacian, there's only one eigenvector where they were different, and everywhere else they were the same. It wasn't the last one, but it was towards the end. And that's, this is basically in the noise part of this. You wouldn't want to use these to help you with the embedding. And this splitting of these is just arbitrary. Yeah, was there a question?
If I consider a graph that has in which edges have weights,
Yeah.
then in that case, replacing the adjacency matrix with let's say a weight matrix,
Yeah.
extend these methods to, would these methods extend to that?
Yeah. So that was the last point I want to make, and that's a great question. So if the edges had weights, how does this work? Well, that just goes into the notion of the adjacency matrix. Instead of just a 1 or 0, you would just be it would have the weight inside of here, and then this degree matrix would just add up the weights. Okay, and yeah, so and things would work. And in fact, the really cool thing is, where would you get these weights from? Well, so these weights, you could think of these as a similarity between the objects. So if I have a notion of similarity between objects, right, and it's going to be the higher the similarity, the more similar they are, the higher the weight, then I can use this to build the adjacency matrix and then do spectral clustering. And it'll give me an embedding that's trying to preserve the similar objects that are more similar to each other. And this didn't need it to be originally in Euclidean space. This could have been with sets. This tells me a way to take sets and with the notion of similarity define them and draw them in 2 dimensions. I create this adjacency matrix, I construct a Laplacian, and then I take the first couple of eigenvectors, and I can draw them in a reasonable spatial location, right? And so this is a really useful tool. Or I can do clustering. I can embed them, and then I can run k-means clustering on them, right? So after I have these notions of similarity defined however I want to define it, I can then run, I can embed them and do spectral clustering or k-means clustering, and either of these will work pretty well afterwards. Yeah.
So I think if this is just used as a graph layout algorithm using the Laplacian, is there any drawback of this as opposed to other layout algorithms?
So this is often a fairly commonly used one. It's kind of a hammer is the drawback. So this is often the first approach, and sometimes what happens, like in this example here, is I get A and D right on top of each other. You don't necessarily want that. And even if things aren't exactly the same, they may end up on top of each other, just because I have a limited number of dimensions I'm using. And so then people will start with this, and then they'll refine it afterwards often. Or they'll use more specialized approaches to try and draw them in other ways. But this is often the first approach towards drawing them, and then they'll use, if that doesn't work, then they'll layer something on top of it. But it's a very common way to actually start drawing these graphs. Yeah. Great. So remember, data collection reports are are going to be due on Monday. So, and we'll post the clustering homework soon, sometimes this week, maybe today or tomorrow.